Far beyond the familiar planets, sunlight becomes little more than a faint glow against an enormous darkness. In that distant region, Voyager 1 continues its journey through space, farther from the Sun than any other human-made spacecraft that is still communicating with Earth. When scientists first imagined what Voyager would encounter beyond the solar system, they expected an extremely thin and relatively quiet environment. Instead, the spacecraft began detecting strange changes in plasma, energetic particles, magnetic activity, and faint waves traveling through the material between stars. These observations revealed something important. The boundary around our solar system is not a simple wall separating the Sun from the rest of the galaxy. It is a complicated region where the solar environment and interstellar space influence one another. The Sun constantly releases a stream of electrically charged particles known as the solar wind. This flow expands outward and forms a gigantic region called the heliosphere. Earth and every other planet in the solar system exist inside this enormous bubble. For many years, researchers expected the outer edge of the heliosphere to behave like a fairly straightforward border. As the solar wind became weaker, material from interstellar space would gradually become dominant. A spacecraft crossing that boundary should therefore move from one environment into another. Voyager 1 reached this frontier in 2012. Its instruments observed a major reduction in particles associated with the Sun, while particles arriving from outside the solar system became much more prominent. The evidence indicated that Voyager had crossed the heliopause, the outer boundary of the heliosphere. Humanity had finally sent a functioning spacecraft beyond the Sun's protective region. But what Voyager discovered afterward was much more complicated than a peaceful transition into empty space. Instead of finding a completely calm environment, the spacecraft encountered fluctuations in particle density, energetic disturbances, and magnetic structures that were difficult to explain using simple models. The boundary was not the end of the story. It turned out to be the beginning of an entirely new chapter. Several years after entering interstellar space, Voyager's plasma wave instrument began detecting a very faint signal around the spacecraft. The signal was weak, but it continued appearing as Voyager moved farther away. That observation became extremely valuable because it allowed scientists to estimate the density of plasma surrounding the spacecraft over long periods. Before Voyager reached this region, researchers often depended on temporary disturbances from the Sun to study interstellar plasma. Those events provided brief snapshots. Voyager offered something different. It provided repeated measurements while traveling through the region itself. The measurements showed that the density of material surrounding Voyager was not perfectly uniform. It changed from place to place, suggesting that interstellar space contains variations and structures rather than being completely featureless. In a way, the space between stars has its own form of weather. Of course, there are no clouds or rain like we experience on Earth. Instead, the changes involve plasma density, pressure, energy, and magnetic fields moving through an incredibly thin environment. Scientists are still investigating exactly what produces Voyager's persistent plasma signal. It could be connected to natural oscillations within the plasma, or it could involve a more complicated process that current models do not completely capture. Voyager discovered the pattern. The difficult part is understanding why the pattern exists. The spacecraft has also shown that the magnetic boundary of the solar system is more complicated than expected. Scientists once imagined that the Sun's magnetic influence would dominate inside the heliosphere while the magnetic field of the galaxy would dominate outside it. Voyager observations suggest that these regions can interact. Near the heliopause, magnetic field lines may rearrange through a process known as magnetic reconnection. During this process, magnetic energy can be redistributed and released. This means the solar system is not completely isolated from its galactic surroundings. The boundary behaves more like an active interaction zone than a simple invisible fence. Voyager also encountered highly energetic particles near this region. The plasma itself is extremely thin, but some of the particles moving through it carried tremendous amounts of energy. That discovery matters far beyond Voyager. The heliosphere plays an important role in reducing the amount of certain high-energy cosmic radiation reaching the inner solar system. Voyager has not shown that Earth's protection is suddenly disappearing, but it has revealed that scientists still have much to learn about how this enormous bubble interacts with its surroundings. The Sun itself is moving through the galaxy. The environment around it is not perfectly constant. Changes in the surrounding interstellar medium can influence the size and shape of the heliosphere over long periods. So Voyager's discoveries are not simply about a distant spacecraft. They also help scientists understand the invisible environment surrounding Earth. Then Voyager 1 faced a problem that had nothing to do with its discoveries. Near the end of 2023, the spacecraft continued sending a signal to Earth, but the information inside that signal was no longer readable in the normal way. Voyager 1 is continuing a journey that began nearly half a century ago, and every new measurement from the spacecraft adds another piece to the puzzle of what lies beyond the Sun's influence. One of the most remarkable things about Voyager's mission is that it has completely changed the way scientists think about the edge of the solar system. The heliosphere is not a fixed structure sitting peacefully in space. It behaves more like a constantly changing environment. The solar wind pushes outward, while the surrounding interstellar material pushes back. The balance between these forces determines the shape and size of the region surrounding our solar system. As Voyager travels farther away, its instruments provide scientists with observations from places that cannot be studied directly from Earth. The plasma surrounding Voyager is incredibly thin, but it still contains electrically charged particles. Those particles respond to magnetic fields and disturbances moving through space. This is why even a tiny signal can become scientifically valuable. A faint change detected by Voyager can reveal information about an enormous region of interstellar space. The spacecraft has also demonstrated that the boundary of the heliosphere can contain unexpected activity. Instead of finding a clean transition between solar and galactic environments, scientists discovered a complicated region where particles and magnetic fields interact. That discovery raises a much bigger question. How does the Sun protect the planets from the wider galactic environment? The heliosphere acts as a giant protective region around the solar system. Its influence reduces the number of some high-energy particles that can travel toward the inner planets. But this protective bubble is not permanent or perfectly stable. The Sun moves through the galaxy, and the material surrounding it changes. If the pressure of interstellar space becomes stronger or weaker, the heliosphere could respond by changing its overall structure. Understanding these changes is important because they help scientists reconstruct the long-term environment surrounding our solar system. Voyager is therefore studying more than just empty space. It is studying the border between our star and the galaxy. And the farther Voyager travels, the more valuable its observations become. There is another reason the spacecraft remains so important. Modern spacecraft are vastly more advanced than Voyager. They have better computers, improved sensors, and far more capable communication systems. But technology alone does not solve the distance problem. A spacecraft designed today would still require an enormous amount of time to travel into the same region Voyager currently occupies. That means Voyager's location gives it something modern instruments on Earth cannot easily reproduce. It is already there. It is already measuring the environment. And it has decades of historical observations that allow scientists to compare how conditions have changed over time. This long record is one of Voyager's greatest scientific advantages. A single measurement can tell scientists what space looks like at one particular moment. Voyager can show how that environment changes as the spacecraft moves through it. That difference is extremely important. Imagine trying to understand an ocean by taking one photograph of the water. You might see the surface, but you would know almost nothing about the currents beneath it. Voyager is more like a sensor slowly moving through the ocean, recording changes along its journey. Its measurements can reveal differences in particle density, energy, and magnetic conditions from one region to another. But Voyager's future is limited. The spacecraft's generators continue producing less power as the plutonium inside them decays. Engineers have already made difficult choices about which systems should remain active. Eventually, there will not be enough electricity to operate all of the remaining scientific equipment. At some point, communication itself will become increasingly difficult. The signal reaching Earth is already extraordinarily weak. Radio antennas on Earth must listen carefully for Voyager's transmissions as they cross billions of miles of space. The delay also creates a unique problem. When engineers send a command, they cannot immediately see whether Voyager followed it correctly. They must wait. Then they must wait again for the response. A simple instruction can therefore become a process lasting many hours. That delay will continue increasing as Voyager moves farther away. One day, a message from Earth and its response from Voyager will take roughly 2 days to complete the round trip. At that point, communicating with the spacecraft will feel less like controlling a machine and more like exchanging messages across an enormous cosmic distance. And eventually, there will be no message to exchange. The exact final moment cannot be predicted with certainty. Aging electronics can fail unexpectedly. A remaining instrument might continue working longer than expected, while another could